Lipids are a class of biochemicals that we do not classify based on functional groups, but we actually classify it based on its physical property. The physical property that defines lipids is that they are insoluble in water and soluble in organic solvents. In other words, they are hydrophobic molecules. What makes lipids not water soluble and soluble in organic solvents is that they have many nonpolar carbon-carbon and carbon-hydrogen bonds and very few polar bonds. And because there's so much nonpolar or hydrophobic characteristics to it, you do not have these dissolve in water. Now, the lipids can be classified into hydrolyzable lipids and non-hydrolyzable lipids. The hydrolyzable lipids includes the waxes, the triacylglycerides, and the phospholipids. These all can be hydrolyzed or cut by water, remember, into smaller molecules. The non-hydrolyzable lipids are not broken down by hydrolysis, and these include the steroids and fat-soluble vitamins. And if you recall, what I just said is all these compounds that are considered to be lipids, they don't have any functional group that we can look at and say, well, that makes that a lipid. It's just the characteristic that they are not hydrophilic. They do not dissolve in water. So we're not looking at one easily defined class. It's really looking at a bunch of classes of compounds. The hydrolyzable lipids are all from the fatty acids. And if you remember the fatty acids, they're carboxylic acids that have long carbon chains on them. And what we're typically talking about are 12 to 20 carbon atoms in that carbon chain. So if you look at this example of a fatty acid given, we have 16 carbons in the carbon chain. There's one in the carboxylic acid functional group, one at the very end, and then 14 in the methylene groups in between. There is a polar portion to it, the carboxylic acid, but its effect is small because the long chain is very hydrophobic. And so as a whole, this molecule is not water soluble. The naturally occurring fatty acids all have an even number of carbon atoms, and we have both saturated and unsaturated fatty acids. The saturated fatty acids, if you remember, we talked about this way back in the carboxylic acid chapter, and we learned there that the saturated fatty acids basically have all carbon-hydrogen single bonds in there. There are no double bonds. All the carbons are saturated with hydrogen so that there are no double bonds in there. The unsaturated fatty acids have a double bond in there. There can be more than one double bond, but there is at least one double bond. They are unsaturated because to form the double bond, you have to remove hydrogen. These double bonds tend to be cis double bonds, and so if you recall, the cis double bonds have a U shape to them. Now, as the number of double bonds in the fatty acid increases, the melting point decreases. So the double bonds make it so they stay a liquid at a lower temperature. And here are two examples of the fatty acids, the stearic acid, and which is a saturated fatty acid, and oleic acid, which is an unsaturated fatty acid. The thing to note is that the stearic acid has no double bonds in it. The oleic acid, which is unsaturated, has a cis double bond in it. Also notice there's an even number of carbons in either of these, and that the saturated fatty acid with no carbon double bond in it is very rope-like, or you can say is stretches out nicely so it can be stacked, and the unsaturated fatty acid is U-shaped and does not stack easily. Waxes are lipids that are esters. They're basically long chains on either side of the ester functional group. So we have a fatty acid and a long chain alcohol. So you might have on the acid side of the ester maybe 13 carbons in addition to the carbon in the carbonyl, giving you 14 in the acid chain. And then you might have 10 or 12 carbons in the alcohol portion of the chain. It makes a very long straight molecule, and waxes tend to stack easily and have high melting points. High melting points because they're long and ropey, like a saturated fatty acid, and they're hydrophobic because all they have is that small hydrophilic ester group and lots of nonpolar carbons on either side of the chain. We can form these waxes by doing a condensation reaction between a fatty acid and the alcohol, and you can see the fatty acid, that R group is the long chain of carbons. We take the hydroxyl group off that acid functional group, and then the long chain alcohol, in which there's many carbons in a long rope off the oxygen there. Take the hydrogen off that alcohol functional group, combine the hydrogen and the hydroxyl group into water, and then join the rest of the alcohol and the rest of the fatty acid into an ester. Waxes can be hydrolyzed in the opposite of that reaction that we just looked at. We can hydrolyze them just as we hydrolyze esters, and we can take water and catalyze it with some sulfuric acid and break it down into the acid and the alcohol. This wax right here is called cetyl palmitate, and you can see there are 16 carbons on the acid side of the functional group. Remember, the acid side of the functional group will have the carbonyl in that chain, and then there are 16 carbons on the alcohol side of this ester. After this is broken down, you have the acid functional group and the alcohol functional group on the two chains. We have the triacylglycerides. These are the fats and the oils. A fat is a triacylglycerol, and an oil is a triacylglycerol. We form the triacylglycerols by taking glycerol and making what we call a triester from 3 fatty acids and the 3 alcohol groups in glycerol. The structure of glycerol is a 3-carbon chain with 3 alcohol groups attached. I showed you this structure earlier in the course, and we called it propane triol. That would be the systematic name for it. You can see because there are 3 alcohol groups, we can do 3 condensation reactions on the alcohol groups, making 3 chains attached to each of those oxygens. So we can take 3 fatty acids and condense them down and remove 3 waters to form a triester. You can see over here that's called a triacylglycerol. And we can see there are the 3 carbons from the glycerol there. Attached to each of the carbons in the glycerol is an oxygen. That oxygen is then attached to the carbonyl, which comes from the fatty acids. You can have 3 different fatty acids. You don't have to have all the same fatty acids, and we actually can have some other groups on there, which we'll talk about in just a little bit. Fats and oils can be differentiated from each other by their melting points. Fats are defined as solids, triacylglycerols that are solids at room temperatures, and we find that fats come from triacylglycerides that are made from fatty acids that don't have double bonds in them. Oils are defined as triacylglycerides that are liquids at room temperatures. And what we find with oils is that they are triacylglycerides that are formed from fatty acids that have a good many double bonds in them. This would be a fat. You can see that the long chain that comes from the fatty acid has no double bonds in them. 1, 2, 3 chains there. Each chain, you can analyze that and look through and see no double bond. So this is a saturated fatty acid triacylglycerol, and this would be a solid at room temperature because of no double bonds, and so we call it a fat. This would be an oil because it is a triacylglyceride, and that double bond puts a kink in there, and that kink makes it so that it doesn't want to stack, and so it has a higher melting point, and it will be a liquid. The fats and oils and the diets have a lot to do with hardening of their arteries, because those things that are fats, saturated triacylglycerides, they will tend to lead to fat deposits inside arteries that then can clog up the arteries either in your brain or heart or legs and cause problems. If you have unsaturated triacylglycerides, they do not tend to form complexes that deposit on the arteries, and because they don't form those complexes, you have a lower amount of fats depositing in the arteries, and they seem to help protect you from things like heart attacks and strokes. We talked about trans fatty acids, which are formed by double bonds that have not been completely hydrogenated, and they release from the catalyst instead of as a cis fatty acid, but as a trans fatty acid, and they're just as bad as the saturated fats. Triacylglycerides can be hydrolyzed by either acids or base or enzymes, because you can hydrolyze them in your body with enzymes. So we can hydrolyze them. When they are hydrolyzed, we break them down into glycerol and the fatty acids. So here the reaction of the triacylglyceride being hydrolyzed with water and sulfuric acid, you can see that they are going to break, and we're going to get glycerol and the fatty acids. The fatty acid shown here is stearic acid. Notice there are 3 fatty acids to every 1 glycerol in a triacylglyceride. You can, when you hydrolyze the triacylglycerides with sodium hydroxide, what you do is you don't get exactly the same compounds. You get a similar set of compounds, but because you use base, you get salts. You can see that we are going to get glycerol from this. The bonds in red are broken, and we get the acids from them, but the acids are present as the salts, And remember how we discussed that fatty acid salts are soap? This is actually how we can make soap, is by taking fats and putting them with something we call lye, which is sodium hydroxide, and boiling it. And when we do that, it breaks apart to glycerol and fatty acid salts, and we call that combination soap, because the fatty acid salts will form the micelles, which will help us clean things. Phospholipids are just lipids that have a phosphorus somewhere in there. Now, the phosphoacylglycerols are a triacyl glyceride that has one of the fatty acids removed, and instead of the fatty acid, you have a phosphate in there, making a phosphate ester, and then attached to the phosphate is an alcohol. Steroids all have the same nucleus or skeleton that's shown here, with 3 6-membered rings fused together, and then a fourth ring that is a 5-membered ring fused to the third 3-member ring. I expect you to be able to recognize the steroid structure. You will see that we have a lot of steroids in our bodies. Cholesterol is a steroid, as well as many hormones like estrogen and testosterone. If you look at the cholesterol molecule there, notice you have 3 6-membered rings fused to each other, and then the 5-membered ring fused to the third 6-membered ring. What differs between the steroids is what are the attachments. For instance, testosterone, instead of having that alcohol group that cholesterol has, it has instead a carbon-oxygen double bond. And so what you see is, as you go from steroid to steroid, they all have those same 4 rings, but the substituents and the bonds within the 4 rings changes. Be sure to do the in-text problems as you read, and these are the end-of-chapter problems that you need to do. I will be posting an online quiz for you.